Welcome to Be Great, where you will discover what greatness is in science, mathematics, technology, and engineering. My name is Amir Ardouf, and I will be your host in this exciting journey. The greatest contributions to our life, as well as our lifestyle, were made by science and technology. Mathematics is the language of science. Mathematics and technology are the basis for great engineering. How do you enter these fields? How do you become great? What knowledge must you master? What are the biggest unsolved problems and mysteries waiting for you to be solved by the power of your mind? Join me as I interview leading scientists, mathematicians, technologists, and engineers and find out. Enjoy. Episode 1, Dr. Mario Livio on astrophysics. Welcome everyone. It's a great pleasure for me to be here with Dr. Mario Livio. I'll read some of Mario's background. Dr. Mario Livio is an internationally known astrophysicist, a best-selling author, and a popular speaker. He is a fellow of the American Association for the Advancement of Science, who worked for 24 years until 2015 with the Hubble Space Telescope. He has published more than 400 scientific papers on topics ranging from dark energy and cosmology to black holes and extrasolar planets. Dr. Livio is also the author of 6 popular science books, including The Golden Ratio, an international bestseller for which he received the Piano Prize and the International Pythagoras Prize, and Is God a Mathematician? That book was the basis for the 2016 Emmy-nominated TV Nova program, The Great Math Mystery. Livio's book Brilliant Blunders, which I happen to be reading, so I have it here with me, was a national bestseller in the US and was selected by the Washington Post as one of the best books of the year. His new book, Why? What Makes Us Curious, appeared in the US in July 2017. Personally, I can say I've had the great privilege of attending Dr. Livio's lectures when I was in university studying physics. That was some 30 years ago. And I can tell you, Dr. Livio, that already by then you were attracting big crowds. And it was one of the most memorable experiences for me as a student. I vividly remember sitting in a hall packed with students sitting in the aisles because there was no room. Everyone wanted to be in your talks. So it's a real honor for me to speak with you and do this interview. So welcome, Dr. Livio.
Thank you. My pleasure.
Before we go into questions, I'll just set the stage. We are here for the most fascinated people, for the most curious people out there. When I think of these talks, I want to talk to these people who really want to take a subject and learn it deeply. Those people who just cannot get enough knowledge in their lives. And today we'll talk about astrophysics, and I want us to talk about what it means to be an astrophysicist and what it takes to be an astrophysicist, and really learn as much as we can from your vast experience. So let's start with the question of the why. Why astrophysics for you?
Well, astrophysics is dealing with the universe, basically. It is dealing with the universe both on small scale, like planets, like Earth, and so on, and also with the universe at large. And it is dealing also with questions of origins. How did the Earth form? How did life start on Earth? How did life emerge in the universe? How did the universe itself start? The fate of stars, of galaxies. So this always fascinated me, and I was interested in these topics, and I thought that in astrophysics you can even find some answers to some of these questions, so that's why.
Do you remember how you found out this is what you wanted to do? Or is it just something that you were always interested in through the years?
No, I actually wasn't. I mean, there are those who started as children, watching, observing through telescopes and things like that. I wasn't like that. We were not a wealthy family. I never had a telescope. It was more that I was really curious, to know why these things are like this. I was very, very observant about the universe around me. And I also, liked mathematics very much. And so somehow it directed me towards physics. But I should tell you that I actually did a master's degree in particle physics, in theoretical particle physics. So it wasn't obvious that I would start with the universe at large. I might have gone with the universe at the subatomic scale, but I was certainly interested in the universe. And that's why, at the end, I ended up in astrophysics.
Okay. I had I spoke about our interview with my 8-year-old daughter, and she she had some suggested questions, and one of them was yeah, one of them was, what makes you feel special to be an astrophysicist? Actually, what she asked originally was, do you feel special as an astrophysicist? If yes, why? If not, why not? But I'll keep it as what makes you feel special doing astrophysics?
Yeah, I'm not sure I feel special. I mean, I think every scientist in every field feels somewhat special in their own field. And certainly there is a lot to be said for other sciences, not just astrophysics. But I touched upon this in my previous answer, that with astrophysics, you deal really with origins. I mean, the origin of the entire universe, the origin of the galaxy, the origin of stars, the origin of planets, and the origin of life. And I think origins always fascinate us. So in that sense, I think this is special. There is also something else, which is, if you ask a person on the street what they are interested in or what they find really exciting, what kind of science, then very often people are excited about astronomy and astrophysics, about space, about, they look at the stars and all these things. I mean, the skies have always inspired, people from poets to painters, and not just scientists. And this is not true for all branches of science. I think people tend to be interested in things like medicine and life sciences because it deals with their own bodies. But maybe next to that, they are interested, I think, in space and astronomy and astrophysics because they find that really exciting, and they are always interested about what happens in the universe.
I think it makes me think what you're saying. Maybe people are really interested in figuring out questions that are maybe easy to ask. And in mathematics, for example, it's very hard to ask the questions because you really need to dig deep into the math before you can ask an intelligent question that's complex and interesting. But what's out there and where did we come from? I think it's very basic to everyone. So maybe it fascinates a lot of people because of that. I don't know.
Yeah, I mean that's part of it. But as I say, I mean everybody sees the night sky, and they see all these objects. They see the moon. Originally, they saw things like the moon, and they see the stars. And then once you have telescopes, you start to see that there is a vast universe out there, and places humans within this vast universe. So people become very interested in this.
Okay. Now, for those watching us or listening to us talk, someone is out there who says, I want to be an astrophysicist. I want to know what it takes, what's the process, what do I need to learn, what kind of experience do I need to gain. So how does one become an astrophysicist?
Well, I guess in the same way that one becomes a physicist or, other things in the exact sciences. First of all, I should distinguish that in astrophysics there are observers, these are astronomers, who look through telescopes and analyze data and, do all kinds of manipulations of data and things like that, and try to extract information from complex data. And then there are astrophysicists who do the theoretical work. They look at what the astronomers discover and they try to develop typically mathematical models that explain and make predictions about what those phenomena mean and how can we understand them. So the preparation for both of those is not identical in the sense that, excuse me, people who are astronomers may even be instrumentalists. I mean, there are people who develop telescopes, and those need somewhat different preparation than people who do theoretical astrophysics. I mean, those people need to understand problems in applied physics, problems that are closer to engineering. They also need a lot of knowledge and understanding things like statistics, because in astronomy and astrophysics, very often the analysis of the results requires complex statistics and statistical method. So they need to study all of those, because today a lot of the analysis of data in astronomy relies on observing many objects, observing millions or sometimes even a billion galaxies and trying to extract properties from those. So that's that. People who do theoretical astrophysics, they need to know areas such as hydrodynamics if they are studying phenomena that involve that. Usually even magnetohydrodynamics, namely also knowledge of magnetic fields. They certainly need to know physics very well, and to know physics very well, because astrophysics involves many branches of physics. I mean, it involves nuclear physics, it involves hydrodynamics, it involves radiation physics, and things of that nature. Then they need to really have a broad education in physics, and of course know also mathematics to be able to solve physical problems and to develop mathematical models. Now, what everybody, of course, needs to know today in these areas is they need to be very, very comfortable with computers, know numerical analysis, very often to be able to handle a variety of platforms and programs and things of that nature. Yes. Now, there are even areas of astrophysics where they now use other things from computer sciences, like neural networks and other things, to, let's say, classify galaxies and things of that nature. Chaos theory sometimes needs to be known. So there are many, many areas of physics and mathematics that one needs to study.
Okay, so when someone when someone starts going through this journey, then obviously they need, like you said, a lot of branches in mathematics and general physics, of course, and then it starts branching out. At what point do you need to make decisions if you're going to be an astronomer dealing with instruments and making measurements, or an astrophysicist?
I think that many people sort of have that feeling from early on. Typically, people who want to be astronomers are people who are more oriented towards experiments, always like to do things with their hands, build things, and are interested in technology. People who become theoretical astrophysicists are more those who were interested more in mathematics, not necessarily very good with their hands. It doesn't mean that they cannot be good with their hands, but they tend to be not those who were the best with their hands. And there are people who like to do calculations and things like that, and they want to know the theory behind things more than to see things and discover them directly.
And how was it for you?
Well, I'm a theoretical astrophysicist. I was always extremely bad with my hands. Was never interested in building things, and was very weak at it. But I liked mathematics, and I liked theoretical physics, and was always sort of interested more in the explanations than in just finding things out.
Okay, so if I continue with the mapping the process, so first there is a lot of learning, which is obviously math and physics, and then what happens? How does it transition into experience?
Well, it is sad to even mention this, but first of all, one needs to find a job,
Okay.
and as an astrophysicist or astronomer, and there aren't that many jobs in that. They tend to be usually in the academia. So I think that people need to realize this, that you really need to be in order to actually get a job in astrophysics, because there are always more candidates than there are positions. So that's a kind of sort of a reality that people have to face. At the same time, I would say, that just for those who eventually don't quite make it to become astrophysicists, having had a broad education in mathematics and physics is a good thing. I mean, and people who even end up not necessarily as astrophysicists end up on their feet usually, in various research companies. I actually know some people who ended up even in the financial world, because the mathematical techniques that they learned are found to be useful even there. But let's go back to those who do become astrophysicists. So they have to find a job, and at that point, they have to, the first step is to find the problems before you try to solve them. So they have to think.
Let me stop you for a second. When you say a job, if you think of the Hubble program, for example,
Yes,
it's not a regular job. It's to the layperson, it's a very famous telescope. It's a huge project. It's not something that's part of academia, as I see it, at least.
yes, but you see, and that's the beauty of it. Today, to use those facilities, you can use the Hubble Space Telescope even if you sit in Tanzania, in principle. I mean, people can apply for time on the Hubble Space Telescope from anywhere in the world. People don't sit physically on the telescope. The telescope is in space. So you can work with the world's best facilities today from wherever you are. So it's not so important. Well, it's important at some level, of course, if you are at a large research center or not. But in principle, you can work with the world's best astronomical facilities from anywhere.
Okay, and you were starting to talk about finding the problem, finding what to work on.
Right, and that's actually at some level maybe the most important part, because you need to find problems that not only interest you but interest others as well. Because if you solve some problems that nobody is actually interested in, then, well, okay, maybe you have some satisfaction, um, some personal satisfaction, but at the end, you haven't really contributed to progress in the field. So you really need to be able to find those problems. You see, when you are a student still, let's say when you do your PhD, then you usually have an advisor who suggests those problems to you. But once you're on your own, um, that's when you start to have to think for yourself, what it is that you want to solve, what it is that you want to find out. And that's very important, uh, because at the end of the day, while solving any problem that is currently unsolved is of some value, um, identifying what the important problems are and those that actually can be tackled and in principle solved is a very important part of the work.
What would you say? I know this could be another 2-hour lecture, but just as an aside, what would you say are the big, let's call them solvable, but big problems today that are the most interesting in astrophysics?
Um, Now, of course, this is somewhat personal, taste. I'm not sure that everybody agrees with everything I would say, but in my view, the currently most fascinating problem in astronomy is, of course, is to find whether there is life out there, and I mean both in the solar system, but that's which is interesting, but not that exciting. But to find whether there is life on planets around other stars, extrasolar life. And of course, in particular, whether there is complex life or what you might call intelligent life elsewhere. I think that that is, in some sense, the biggest problem in astronomy and astrophysics today, to find out this. But there are other problems.
Is it considered solvable other than going there, which is
Oh yeah.
so?
Oh yeah, yeah. Oh no, this is fantastic actually, you see, because we are now, for the very first time in the history of humankind, we are, I would say, at most 2 to 3 decades away from being able to either answer this question with a yes or no, or if not to answer it directly, then at least to put some meaningful constraints on how rare or not life is. Namely, I believe that within at most 2 to 3 decades, we would either find life elsewhere, and by that I mean not necessarily complex life, but at least some primitive life, or we would be able to say things such as, oh, on all Earth-like planets that orbit sun-like stars in that habitable zone, which is not so cold, not so hot, so that it allows for liquid water on its surface, no more than 10% of those have life in them, or something like this, in case we don't find anything. Mm-hmm. So I believe this is within our reach, well, maybe not my personal reach, because I will probably not live 20 or 30 more years, but within your perhaps lifetime, I think we will know the answers to that. So I think that is, in that sense, a fantastic stage in the history of humankind. Now, there are other problems. For example, there are two forms of dark entities which we don't fully understand. I mean, there is something we call dark matter, which forms the scaffolding onto which the universe builds its structure. And it surrounds us all, and all galaxies and all clusters of galaxies. But we have not yet discovered, the particles that dark matter is made of, or whether or not we misunderstand the whole thing and there is no dark matter, but we need to change our theories of gravity. But in any case, we don't understand what exactly that is. The second thing is dark energy, which permeates all space and is causing the cosmic expansion to accelerate. And on that, we have no idea what that is.
Yeah.
So these are two huge problems that need to be solved.
Okay, interesting. Like I said, this could be complete lectures in themselves. So,
Of course.
But it is important for me to talk about what are people going after and what's interesting and what's what they aim to.
Right.
Let's talk a little bit about your career as an astrophysicist. What were your best decisions, key points in your career that you consider important?
Well, first of all, I think to go into astrophysics in the first place was a good decision because, this, as I expected, turned out to be a very exciting field. And during my lifetime, we have seen very, very exciting discoveries. Just to mention a few, this dark energy that I was talking about was discovered only. Yeah, was just discovered just in 1998.
Yeah.
So these are discoveries during my lifetime. So to do astrophysics in the first place was I think a very good decision from my perspective. To work on Hubble I worked at a large research center, and it allowed me access immediate and rapid to new discoveries by the telescope. So that was very good. I would say those were probably two important decisions. I mean, one to go into the field to begin with, and the other, to join a very central research facility.
What would you say, or how you would describe a typical day in the life of an astrophysicist? Obviously, it's different for everyone, but
yes,
someone needs to sit
day.
down and doesn't really know what it means. I come to work. What happens?
Well, again, I think there is somewhat of a difference between a typical day in the life of an astronomer, an observational astronomer, and a day in the life of an astrophysicist.
Okay.
An astronomer, first of all, makes proposals for observations. So a lot of time is spent on writing those proposals, identifying what targets to observe, and so on, and then propose those proposals to various telescopes, to various facilities. Once they obtain time on those telescopes,
obtain time means getting funding for it, or just someone agreeing that it's important enough or interesting enough?
Well, basically, if you take something like Hubble, then let's say every year there is a call for proposals for the telescope. The telescope receives something, more than 1,000 proposals typically per cycle. And then panels of experts sit and sift through those proposals, read them very carefully and rank order them, because not everybody can get time. On the average, maybe 1 out of 7 proposals gets accepted. So basically, they decide which proposals get accepted. And then that means, once your proposal is accepted, it means that the telescope will actually will make the observations that you suggested. So that's how that works. And it works with other facilities in a similar manner. And then once you make the observations, or, the telescope makes the observations, then the people receive the data, and then they have to spend a lot of their time on data reduction and data analysis. And eventually, to write up their results in the form of scientific papers. So that's what they spend their time on.
These are the astronomers.
Yes, theoretical astrophysicists, on the other hand, well, sometimes they also get involved in proposals because in most proposals, astrophysicists are also involved because you need to justify why you may want to make the observations, and astrophysicists provide sort of the physics background and what one expects to get out of those observations. So they are involved somewhat in that, but not to the same extent as the astronomers. They certainly don't deal typically with the data directly. Rather, they see the results that come out of the observations as those are being published. And once they see the results, they try to construct theoretical models that explain those results, or see whether those results agree with existing models, or try to make new predictions about what other observations could be doing and things like that. So typically, a theoretical astrophysicist sits in her or his office. They read all kinds of scientific papers, and they try to build mathematical models and very often run them as simulations on computers. So basically, you see them sitting much of the time in front of a computer screen.
Yeah. Okay. So they really take measurements and results from the astronomers, and they choose what to work on, and try to build a model. Really.
Right.
Okay.
Based on their expertise and so on.
Okay. That's great. I think it's again, to someone who doesn't understand how it works, to you it's a regular day and this is how it is. But it's to me, listening to this, it's not obvious at all. I wouldn't know how to explain it, and I don't think you hear many people talk about it. Really, you talk about what's being discovered, but you don't get to hear a lot about the process and how it happens.
Well, there is a lot of hard work that leads to the discoveries, a lot of hard work, both on part of the astronomers and on part of the theoretical astrophysicists. Now, today, because the projects tend to be large, astronomers very often work in large collaborations. So very often now, if there is a big astronomical project, you will see that there are dozens of people who at the end, have their names on the publication. With theoretical astrophysicists, it's usually not like that. It's hard to do theoretical work in huge groups. So typically you would see collaborations only between a few people who do theoretical work.
Yeah. Okay. All right. Let's talk about some more about astrophysics and really reaching great results. If you had to think who are the greatest astrophysicists, what would you say?
Well, I probably wouldn't dare to tell you the greatest living astrophysicist because I don't want to annoy anybody.
To exclude.
But I can tell you, but I can tell you. You see, we're not that long into the 21st century. I can tell you about the 20th century.
Okay.
So in the 20th century, so first of all, of course, Einstein at some level was an astrophysicist because his theory of general relativity is what explains how the universe at large is behaving, and that's today parts of cosmology and astrophysics.
Is it true to say that he did that without the measurements, rather than getting measurements and then figuring out a theory?
No, he did that really with the power of his mind in many ways. But of course, he later heard about observations and actually included those in his things. Yes, but he started with the power of his mind. But many phenomena. I mean, not just how the whole universe behaves, but such things as gravitational lensing, the fact that mass can actually bend the path of light rays, and as a result, it works like a lens. That's also something that Einstein contributed, and that is a technique that is being used a lot in today's astronomy and so on. So at some level, he did much of the work for that forms the basis for today's cosmology and astrophysics. Yes, I should mention, perhaps I didn't before, that some people distinguish between cosmology and astrophysics. Cosmology is that area which deals with the universe at large. Astrophysics, if you want to make the distinction, deals more with the individual objects, with galaxies specifically, with stars, with planets, and so on. But of course, there is no hard boundary between the two, and so on. Now, so Einstein, yes. Then, in way of theoretical astrophysicists, Arthur Eddington was one of the greatest of the last century. He formulated some of the very basics of our understanding of stars in particular and what they do. And Fred Hoyle, both of them British, by the way. Fred Hoyle is a person that contributed a lot to our understanding of what powers stars, all the nuclear actions at the centers of stars, and how all the elements are being formed and forged inside those nuclear furnaces at the centers of stars. So I would say those three really stand out as theoretical astrophysicists. In terms of astronomers, then of course Edwin Hubble stands out. He not only discovered that the universe is expanding, but he also was involved with classification of galaxies and things of that nature. Showing that galaxies are of different types, and he also was involved actually with the discovery that there are galaxies other than the Milky Way. Another great astronomer of last century was Alan Sandage, who was in many ways Hubble's successor, even worked with Hubble, and did a lot of fundamental work, again, both of the expansion of the universe on stars and on many, many aspects of astrophysics. So, I would say those names stand out in my mind. Of course, there are many others who made enormous contributions.
Of course, yeah.
But those really quite stand out.
And when they stand out, if you say someone was or is a great astrophysicist, what does it mean to be great in your mind?
Well, it means that they made very, very significant and fundamental contributions. That's what I mean. So we all
so the questions
benefit
you were
from what they contributed.
So the next great ones are those who will answer these great questions that you spoke of, for example.
Yes, that's right. But as I said, because people tend today to work in larger collaborations, discoveries are likely to come not from a sole individual, but rather from some group or things of that nature. Now, of course, these groups are typically led by somebody, but they are still relatively large groups. And in general, I would say that we have reached a stage where the field is very observationally driven. I mean, you need to find the astronomical discoveries and then explain them. Not so much anymore that theorists come up with something completely new that nobody thought of, and only then that's observed. It is more driven by the observers. Maybe I should mention another development that is more typical of the recent decades and will certainly be typical of the future, and that is that the fields of astronomy and astrophysics and high energy physics have become very close together. At this point, to solve the universe, we understand that we need to understand both the large scale and the subatomic scale. Today, a number of the cosmologists are what is now called astroparticle physicists. Namely, they deal with things in astrophysics, but also in particle physics. So, for example, I mentioned that we need to discover the particles of dark matter. That is done by traditional, sort of more particle physics types than astronomers. But the discovery, the main meaning of it is for astrophysics. So these are the types of things that are happening today.
I see. So you expect these discoveries to be made by particle physicists?
Partly, at least, yes.
Yeah, partly. Okay. A related question to all of this is about science in general. What, in your opinion, will make science go faster? What I mean is make more discoveries happen and more quickly, if there is anything like that.
Well, again, it is perhaps somewhat unfortunate, but we have reached a situation where funding has become very important. You see, I mean, we're no longer in the days where Ernst Rutherford could sit with one assistant and do a big experiment. Experiments today require very large and very costly facilities. The James Webb Space Telescope, which would be the next big telescope following Hubble, is costing at the order of $8 billion. The next particle accelerator to come after the Large Hadron Collider in Geneva now is likely to also cost in the neighborhood of at least $10 billion. So you're talking now to make the real breakthroughs, you need scientific facilities that tend to cost more money than a single small country can sustain. So what you need is larger collaborations. Only things like the entire European community or the US, can support such large projects.
Financially.
This is not to say that there isn't work to be done by smaller satellites and so on. And indeed, countries such as Japan, keep launching interesting satellites that do good work. But the very large projects require a lot of funding and a lot of collaboration.
Okay. Is there other elements besides the funding?
Well, collaboration. It's not just the funding. It's collaboration. We should also realize that science is, very international. So at some level, we shouldn't care if the discovery is made in Europe, in China, or in the US, as long as it advances science. So science should be open to everybody, and that is part of what science is all about. There are other things that will help. I mean, certainly the availability of more computing power helps. The development of new technologies helps for sure. And there may be technologies that we're not even aware of. Now, when you say science in general, if you mean by that also other branches of science like the life sciences and so on, then again, of course, funding is important there. There as well, and technology is extremely important there. Um, we can now, do sequencing in much shorter time and much less money than when it was first done. And and things of that nature tend to evolve, excuse me, with the technology. So, but the
So
technology developments,
advances in technology would in turn lead to more discoveries, or
right, in technology, in computing, in
yeah,
things of that nature.
yeah.
Yes.
Does this apply to astronomy and astrophysics as well?
Oh, absolutely. Yes, of course. I mean, the data sets become huge. I mean, there is so much talk about big data, right?
Yeah.
And astronomy is a very good example of big data. The telescopes of the future are generating and will generate enormous amounts of data. And you need all the power you can have in order, and the techniques to analyze that data and, get the most out of it.
So for someone to contribute, they can contribute in the technology area as well as the actual
Absolutely.
measurements and the analysis.
Right. And,
Yeah.
and the why I said, the more the instrument types or the computer science types and so on, they can definitely contribute.
Okay, great. Um, maybe maybe a final question. Before we wrap up, I would really love for you to speak a little about your work now, your books, where people can find out more about you.
Well, I still continue to do research, even though I'm formally retired.
Okay.
And my research at the moment, I would say, concentrates more, although not exclusively, on extrasolar planets, and again, the relation to the emergence of life in the universe. But it just so happens that I also finished a large review on these stellar explosions called supernovae and so on. So I do other things as well, but I'm very, very interested in the question of extrasolar planets and life. And that's where part of my research goes.
And where does one find your work?
Online. It's all available online. In astronomy in particular, there is an archive where you can find all the papers that I've published and all the papers that other astronomers have published. It's online, and astronomy is actually more advanced in this respect than almost any area of science. That these archives are very complete, and they give access to all the scientific papers that have been published.
Excellent. I'll make sure to include links to that as well.
So that's one thing. So this is in terms of personal research. In addition, I continue, of course, to write books. So my last book on human curiosity was just published this year, and actually the paperback is about to appear next month in May. The paperback edition of What Makes Us Curious will appear. I think the official publication date is May 22nd, if I'm not mistaken.
Okay, great.
But of course, I work already on a new book, which means I work on the research for the new book. Being a research scientist, the part that I enjoy most in writing books is the research part. And that takes me actually most of the time to do the research. Now, because it's in the early stages, I tend not to say at this stage, what this book will be about. Yes.
All right. We'll leave it as a surprise.
Because it's too early. I mean,
Okay.
It takes me typically 3 to 4 years to write a book.
Yeah.
So we're talking, publication probably around 2021 or thereabouts. Maybe 2020, but certainly not before. So I tend not to talk about this so early. But yes, that takes a lot of my time. I'm currently very deep into research for this new book. And I'm very excited about this. I work literally morning to night uh, on this research. So yes, so there is still a lot to be done.
Yeah, so that, first of all, it's wonderful to hear, and I would add my own recommendation to simply search your name in YouTube.
Yeah,
There is
I'm
so
on.
much material.
Yeah, I'm on
Um,
YouTube. I'm on Facebook.
yeah,
I have a sort of public page on Facebook. I'm on Twitter. People can find me. My Twitter handle is what is it actually? I believe it's Mario underscore Livio or something like that
okay,
on Twitter. Um, and there is a Wikipedia page about me, and it gives links. Of course, my books are all on Amazon, but can
yes.
be found in all bookstores and so on. So
Excellent, excellent. And I'll make sure to add in the notes for our interview all the links and everything, so everyone can follow you from all directions.
okay,
Um, so just to end, I'll say again personally that it's a real privilege for me to talk to you. It's a you know, you've been in my mind for tens of years already, and I remember when I first saw one of your books. I think it was The Golden Ratio in a bookstore, and suddenly wow, this is the name. You know, this is who I learned with at university and so on. So personally, again, it's a real pleasure for me, and thank you very much. It was really wonderful. Thank you.
thank you for having me. It's been a pleasure.
Thank you.
Bye bye.
Bye bye. Thank you for joining me. Make sure to subscribe to the YouTube channel or the podcast, and I'll see you in the next episode.